Hello everyone, welcome back. In this video, we are going to discuss about techniques to solve data skew. And the first one of it is AQE, which stands for Adaptive Query Execution. And this was recently introduced in Spark 3.0. And the other technique is broadcast joins. So this is going to be more in context of solving data skews, how broadcast join can help solve data skew. So let's get started. So what exactly is AQE? AQE, as I said, stands for Adaptive Query Execution. What it means is that Spark on its own is going to use runtime statistics to basically select the most efficient query plan, right? So these runtime statistics can be your number of bytes read, basically the size of your input data set. It can also be the number of partitions and so on. So using these runtime statistics, it is going to choose the most efficient query plan. And the kind of tuning that AQE gives us is amongst these three. The first one is tuning shuffle partition, simply meaning that let's say you have 200 shuffle partitions by default and you have a data set. When you're doing a join, let's say you have a data set which only has 15 distinct keys. So this would simply mean that the remaining 185 partitions are going to be empty, right? So what Spark does is that it is going to coalesce all of the partitions into 15 partitions because there are only 15 distinct keys. So this reduces the number of shuffle partition, right? So that is the first optimization that it does. The second one is optimizing joins. So it basically converts your sort merge join into a broadcast join. As we all know that sort merge joins are operation heavy. The first operation that a sort merge join does is a shuffle. Shuffling involves data transfer all over the network, right? While broadcast joins doesn't involve a shuffle, right? So that is the reason why AQE does a lot of benefit it by converting a sort merge join to a broadcast join. The third one and the most important one to us is optimizing skewed joins. So what AQE does is that it is going to convert the large partition, the skewed partitions in a short merge join into smaller partitions. So it breaks up those larger partitions into smaller partitions. So let's say you have partitions like this. It is simply going to break up this partition into a smaller partition, which can easily be processed by your codes, right? So these are three of the optimization that AQE provides out of the box. Let's also try to have a look at the Spark documentation to understand more about AQE. So let's move to the optimizing skew join. And what we see over here, this is the most important part. So the property name is Spark SQL adaptive skew join enable. If you set this to true, what is going to happen is that Spark is dynamically going to handle the skew in a sort merge join by splitting the skewed partition, right? And in order to make this happen, you basically need to set two of your properties to true. The first one is Spark SQL adaptive enable to true, and the second one is Spark SQL adaptive skew join enabled to true. Okay, so let's look at an example to understand how AQE can help us to resolve data skews. So here I'm just trying to do the imports and also set up a Spark session. And my objective here is basically to join two data sets, which is the transaction data set and the customer data set, to basically analyze how the join is going to look like with and without AQE. So let's go ahead and do that. Let's see how the transaction data set looks like. It basically contains the customer ID, the start date, transaction ID, and then some other details, right? And let's have a look at the customer ID, some details about the customer, and then the home city of the customer. Now, before we do a join, let's try to understand how does the distribution of data look like at the customer ID, at the join key. Okay, so here we see that there is one customer ID which has a lot more transaction than the others. So this simply means that whichever partition is holding this customer ID is going to be skewed. So let's try to see how the sort merge join behaves. So we are by default setting the auto broadcast join threshold to -1 because we want to disable it and we want to do a sort merge join. Let's also see how it looks on the Spark UI. Okay, so here you've read in two datasets already, and now there is a join going on, which is this one. Okay, so it's already completed. And let's have a look at the event timeline. Okay, so here you see there is a partition which is skewed, and processing this partition takes a lot of time. So the executor computing time for this partition is a lot. Now let's try to switch on AQE. So based on the Spark documentation, we've set these two properties to true, and let's try to do a join. Okay, as you can see over here, the timing improvement is not a lot. It's 10.9 versus 11.8. But let's have a look at the Spark UI just to understand what are the differences between the two. So I believe this is one of the join, while this one is the other one. Okay, so this is the one with AQE and this is the one without AQE, right? So let's try to have a look at the stage in which the join happens, and you see that there are four partitions over here. Well, let's have a look at this one. Okay, here you see there is one large partition while there are several small partitions. Let's try to look at the SQL, the query plan, to see something interesting. So this is the query plan for the AQE one. Let's also have a look at without AQ. Okay, this is without AQE. So here you see that there is at first a scan of the parquet, then there is a shuffle, and after that shuffle you have a sort and then a merge for the sort merge join. An important thing to note here is that the number of partitions, the number of shuffle partitions is 200, right? For the first dataset and for the second dataset. Now let's compare it with the one with AQE. You see that there is a scanning of the parquet and there is an exchange which again has 200 partitions over here for both the dataset. Now you would see there is an additional step which is called AQE shuffle read, and what it does is that instead of 200 partitions it reads in 4 partitions, right? And for that reason you would see 4 partitions over here, 4 partitions over here, right? And you also see 4 partitions over here. So from the exchange there is another step which reads in 4 partitions. So what it effectively does is that it reduces the number of partitions. So lesser partitions would mean lesser tasks, and lesser tasks would mean lesser resources to be employed to work on those tasks, right? So that is one of the optimizations that AQE does. Another thing that is interesting to note is that the minimum time for processing a partition is 2 seconds while the maximum is 7 seconds. So there is a gap of 5 seconds between the minimum and maximum. While if you look at the task without AQE, it is 11 milliseconds minimum and 7-second maximum. So this implies that After a certain amount of time, and basically by maybe after the 75th percentile time, most of your resources would be sitting idle. And because the gap is larger, it would also imply that a good amount of your resources would be sitting idle after a certain amount of time, right? While only limited set of cores would be utilized. So these are some of the advantages that AQE provides you out of the box. You just need to enable the two properties that we saw on the Spark documentation to true. It's also very important to note at the same time that AQE may not be the best option in a lot of cases, right? So you would need to manually intervene and then do some of the tweaking and optimization yourself. Yeah. So the second approach to solve a data skew is by using broadcast join. It is considered to be better as compared to a sort merge join for certain cases where one of your table is smaller as compared to the other table, right? Let's try to get into the internal workings of both a sort merge join and a broadcast join to better understand how it helps us in fixing data skews. So a sort merge join basically involves three steps. The first one is a shuffle, the other one is a sort, and the last one is a merge. The shuffle being the costliest operation because it involves a data transfer all over the network, right? So now let's take an example on two data sets being joined through sort merge join. So let's assume that we have three executors, executors 1, 2, and 3, and we have two data sets whom we want to join, a transaction data set and a customer data set. And they are supposed to be joined on customer ID and customer ID, right? And we have one partition each of the data sets on each of the executors. So this is partition P0, P1, P2, and similarly for the others P0, P1, and P2. Now, when we want to join both of them, the first operation, as we said, is going to be a shuffle. And shuffling would mean that there would be some transfers of data over the network, and these keys would end up in different partitions, right? And let's try to define the logic on which partition would the keys go to. So let's assume that the shuffle partition is 3 in number, right? And the logic by which we define that this key is going to go to which partition is simply key mod the shuffle partition, right? So we simply do key mod 3 and we decide that okay, this key is going to go to this partition. Okay, so a very important point to note is that the rule that I mentioned, we decide which key is going to which partition, is something like this. So in reality, there's a little bit of difference. Instead of the key, what we do is that we do a hash of the key mod shuffle partition, right? So this is the rule, the actual rule that is applied. Now if you're joining on multiple keys, and those keys can be either an array, string, or an integer, you do a hash. I mean, Spark internally does a hash on all of those keys, and then it does a mod shuffle partition. So this ensures that you're going to get an integer irrespective of whatever column these are. So this gives you an integer. Now in order to make sure that this integer falls within your bucket range, falls within the number of buckets that you have, right? The number of buckets in shuffle partition, we simply do a mod shuffle partition. Mod shuffle partition, right? So this is how it works in reality, but for simplicity what we are going to do is we are only going to refer to key mod shuffle partition from here on in the video. So for example, this customer ID 3 mod 3 is 0, it is going to go to the 0th partition. This is going to go to the first partition. This is going to go to the second partition. Similarly for this 0, 1, 1. And then similarly for this one would be 0, 1 and 1. Now this would basically reflect as this 3 basically going over here, 6 coming over here, and then that is how you would see the rest of the steps, right? So you would see that 1 to 19 basically comes over here, whichever had a remainder of 1, and 5 basically comes over here, and similarly for this data set as well, right? So the shuffling has already happened, and the same keys are sitting on the same partition, right? Whichever key had the same modulo, they are sitting on the same partition. Now, after shuffling has happened, we are going to do the sorting. And I have not shown it explicitly in this diagram, but you see that this data set is sorted. So after shuffling, sorting happened, and these data sets are sorted. These two data sets are sorted. All of them are sorted, right? Now the last step over here is a merge. Merging is very simple. You basically compare these two numbers. Basically there is a pointer at the two data sets, and if the number at those pointers match, then they are going to be joined. Those rows are going to be joined. So this row is going to be joined over here. 6 and 6 match, so it is going to be joined over here, right? And similarly for all of the partitions over here and here. So the final result that you see over here basically looks something like this. You see the final data set looking something like this. So this is the merged data set. Here is the transaction data frame, and here is the customer data frame that has been merged. So we see that in a sort merge join, the data was first shuffled, sorted, and then merged, right? A couple of costly operations, right? Now let's try to compare it to a broadcast join. So we've taken a similar scenario and a similar data set. We have 3 executors again and one partition of the transaction data set. This is partition P0, P1, P1 and P2. Right? The same partition as we had earlier. Now what we say over here is that we are going to send one copy of the customer's data frame to all of the executors. Now the customer data frame was a very small data set, and that is the reason why we do that. So we are going to send this to all of this over here, right? And then there is going to be a join between this customer dataset.id and transaction.customer id, which is also going to yield you the same result as you see over here, the same that we saw in the earlier example, right? Now a very important point to note over here is that broadcast joins are immune to skewed input dataset, and the reason for that is you have complete flexibility to partition it the way you want. There is no compulsion that you have to partition it by the join keys. When is a skew going to happen? When you partition it by the join key, right? Because remember that a customer there was a customer id which was abnormally distributed, and it has a lot more transaction than the other customer id. So if we partition by join key, then there is a possibility of skew. But these data sets, right, these partition that we have over here, we have complete flexibility to partition it as in the way we want. So we can simply do a repartition 3, and it is going to evenly partition these over here, and then you're going to send the customer data frame over here, and then the join is going to proceed, right? So then there are going to be no skews because these data sets are already evenly partitioned. So this is how a broadcast join is going to help you, right? Now let's try to look at an example. So we are going to take the same example between the transaction and the customer data set, And before we go ahead, I've just enabled auto broadcast join threshold to 10 MB. That means any dataset with size less than 10 MB, go ahead and do a broadcast join, right? And let's see how much time it takes. Okay, so it takes 3.2 seconds, which is just one third, almost one third of what was being taken in AQE, right? I hope you are able to understand how broadcast joins can be very beneficial in solving data skew. Okay, that's all about AQE and broadcast joins. I've discussed about salting, which is another very important technique to solve data skew, which you can refer to in this video.